Yes, okay. Okay. This is the most general case, and in this case, the rejection rules once again involve the percentile t distribution. Excuse me. I understand what your question is. Can you guys stop talking, please, while I teach? Please, if anybody is talking to your friends or something, could you please stop talking, because it seems they are. Hello, guys. If you. Hello, guys. Can you hear me? If you're talking to your friends, please press the mute button. Okay. Anyway, so in this case,
aquí vengo porque me da la gana. He estado en la parte de atrás del coche tuyo. Y en la parte de adelante. No me gusta la gente. Esto es seco, ¿eh? Es un MP3. Me he comido un trozo de mandarina.
Hello, guys. Okay, this is the most general case where the rejection rules once again. The rejection.
Que todo mal, ya no hay nada que hacer.
Lucia, are you there, Lucia? Can you press the mute button? Okay, thank you, Lucia. Okay, all right. So this is the most general case, and the corresponding rejection rules. Yeah, thank you. The corresponding rejection rules involve the percentiles of the t distribution once again, and where a is the degree of freedom given by this complicated expression, and sx squared and sy squared are the sample variances. So sx squared is the sample variance for the first sample, and sy squared is the sample variance for the second sample. And in all three cases, that is case 1, case 2, case 3, we are assuming that the two samples are coming from a normal distribution with mean mu x. So the first sample comes from a normal population with mean mu x and variance sigma x squared, and the second sample comes from a normal population with mean mu y and variance sigma y squared, and both samples are independent. So that assumption holds for all three cases. And case number 4 I considered on Tuesday is this one. Where we are testing for equality of population proportions. So for example, it could be that, like, for example, you may want to compare, for example, the proportion of smokers in UK for the male population and the female population. So whether you like to know whether they are equal or not equal, for example, right? That the proportion of smokers among males is equal to the proportion of smokers among females, or not. All right. So in this case, you have two samples once again coming from Bernoulli populations. With the first sample comes with proportion px. The second sample comes from a Bernoulli with proportion py, and we are assuming that the samples are independent, and we are assuming too that the proportions px and py are known. And there are three cases, three hypotheses, and the corresponding rejection rules are the ones I have listed here. Okay, and they involve the percentile of the normal distribution. I'm sure you know how to read the normal table. Okay, so these are the four. So just to summarize one more time, there are four tests in the two sample case. The first one is the testing for equality of population means when the variances are known. The second one is the testing for equality of population means when the variances are unknown but equal. The third one is testing for equality of population means when the variances are unknown and not equal. And the fourth one is this one, where testing for equality of population proportions. Then I started to do an example on Tuesday, but I didn't have time to start. I didn't have time to, I didn't have time to do it. All right, so I asked you guys whether you have the time or not. Okay, but all right, now obviously I don't know whether you guys had the time to do it or not, but any case, let me show you how to do it. Okay. Okay, let me erase this. Okay, so let me excuse me. Yes. Okay, so I'm going to show you how to consider. So you have two independent random samples. The first one is coming from a normal population with mean mu(x) and variance 1. The second one comes from a normal population with mean mu(y) and variance 2. And we are testing this versus this. So I want to. So the question is this: if the question is this: if the rejection rule is that x bar is the sample mean for the first sample minus y bar is less than a constant k, and then find alpha and beta. Okay, so alpha, remember, alpha is the probability of type 1 error and beta is the probability of type 2 error. So let me first start with alpha. Alpha is we are rejecting the null hypothesis when mu(x) is equal to mu(y), right? Which is the same as saying the probability of x bar minus y bar is less than k, given that mu(x) is equal to mu(y). Okay, guys. Now, remember that we are assuming that mu x, the first sample, comes from a normal population with mean mu x and variance 1. All right, so x bar, what distribution will x bar will have? You probably remember this if from long time ago when we did this ages ago. I don't know whether you guys remember or not, but if you look back in the notes for the normal distribution, this is what you will see. Okay, this is what you will see. Okay, so I use the fact that if you have a random set, so this is the, I mean, if you don't remember this, I can write it down in a red box. If you have a sample x1 to xn IID from, this is a property I talked about a long time ago, right? If you have a sample like this, right, then x bar, the sample mean, will have a normal distribution with the parameters mu and sigma squared by n. Right, this is, if you look back in the property under the normal distribution, you will see this, right? Okay, guys. Oh, sorry, yeah, you're right, sir. It should be 2n, yeah, not 2m. I'm being sleepy today, I don't know why. Yeah, you're right, thank you. And thank you for pointing that out. It should be 2 divided by n. Okay, so that becomes equal to the probability of, now because the two variables are independent of each other. Remember, a normal linear combination of two normals is also normal, which is something I taught a long time ago to you guys. So this will be mu x mu y. That will be the mean, and the variance will be 1 over m plus 2 divided by n, right? So this will be the normal variable less than constant k, given that mu x is equal to mu y. Okay, you follow me? All right, now because mu x is equal to mu y, this must be the probability that n 0, a normal variable with 0 mean, and variance 1 over m plus 2 over m is less than k. Now we don't need the conditioning anymore because we have used, we have used the conditioning that mu x equal to mu y. So we don't need to keep it anymore. Okay, so that's why I remove the conditioning in this step, right? Because we have used it. Okay. All right. Now, in the next step, I'm gonna. Hello, guys. Welcome. In the next step, I'm gonna make the variance into 1. So that will be, so what I need to do is I need to pull out the square root of the variance. So you see, let me do it like this. Okay, what I'm gonna do is I'm gonna divide both sides. I'm gonna divide both sides by the square root of the variance. Okay, so now the left-hand side will become the standard normal variable. Okay, and the right-hand side will become, you can simplify it a little bit. It will be k times mn divided by n plus 2m. All right, so this is what you get. So this will be equal to phi. Phi is the CDF of the standard normal at okay, so this is the, so just to summarize, what we have shown is that we have shown that alpha, the probability of type 1 error, is equal to this. Okay, is that clear, guys? Or are you okay with this or no? Any questions so far before I do the next part? Guys, are you okay? All right, the next part of the question is to find beta. So beta, remember, is the probability of type 2 error. So it's the probability of accepting the null hypothesis when H1 is true, which is mu x not equal to mu y. Okay. Now accepting is the opposite of rejecting. So now we initially said if the question we reject the null hypothesis if x bar minus y bar is less than k. So we will accept it. We will accept it if the opposite is true. So we will accept it if x bar minus y bar is greater than or equal to k. Okay, so this is the rule for accepting. All right, so we need to work this. All right, let's see how we can do this. So I'm going to use the same argument as I did for alpha. So I'm going to use the property which I mentioned a few minutes ago, that x bar will have this following distribution. All right, and y bar will have this distribution. All right. Okay, guys, you okay? Now the difference of two independent normal is also normal. So using that property, I will say that this is the same as the probability that a normal with this mean and variance equal to 1 over m plus, excuse me. Yeah, sorry. Yeah, it should be 2. Yeah, you're right. I'm being really bad today. Should be 2. You're right, sir. It should be 2 over n. So it should be 2 over n. So 1 over n plus 2 over n greater than or equal to k, right? Given that mu x is not equal to mu y. Okay. Okay. Now the next thing we need I'm going to do is I'm going to standardize what the normal variable on the left hand side. So I'm sure all of you know how to standardize a normal variable. What you do is you subtract the mean and divide by the standard deviation. So that's what I'm going to do. So I'm going to just be patient with me, guys. So I'm going to okay, let me do it in a step at a time. So I'm going to first subtract the mean, which is mu x minus mu y, right, on both sides. Okay, given mu x is not equal to mu y. Okay, so if you do this on the left hand side, you will get a normal variable with 0 mean and variance equal to this, greater than or equal to k minus mu x plus mu y, given okay, and in the next line, I'm going to divide by the standard deviation, which is the square root of the variance, right? So I will divide both sides. All right. Okay, guys. And in the next line, it's clear that what you have is a standard normal variable. So this becomes the probability that the probability of n01 is greater than or equal to k minus mu x plus mu y divided by this expression here. Excuse me. Okay. So you can write this as 1 minus phi of k minus mu x mu y. Okay. So this is the expression for beta. Okay, so just to summarize, so what we have shown is that beta, the probability of type 2 error, is equal to this one here. All right. All right. Any questions, guys, on what we've done so far? So that's just one example. Just one example on the material that we covered on Tuesday this week. All right. Any questions, guys, so far? Hello. You okay? All right. Now let's do another example. Hopefully we have the time. And by the way, after this class, we have two example classes from noon to 1 p.m. and 1 p.m. to 2 p.m. We will go through the example sheet number 10, right, which is on the website, of course. So please do come to those example classes if you haven't been. If you haven't been to those, the ones yesterday. Yesterday we had two example classes too. So normally, I mean, you may want to stay for the 2 hours, because like what I do is normally in the first hour I will do the first 2 or 3 of the question, and in the second hour I will do the remaining 2 or 3 of the questions. So you may want to, I mean, unless you have something else to do, you may want to stick around for the 2 hours example class. Okay. Okay, thank you. So example 2. Okay. So it's example 2 is the same as example 1, but we consider it testing this hypothesis with okay, guys. So it's the same as example 1, but we are testing mu x equal to mu y versus mu x not equal to mu y, with h0 rejected if the absolute value of x bar minus y bar is greater than a constant k. And the question is, once again, to find alpha and beta. All right. Okay, let's see how we can do this, at least part of it. All right, so let's start with alpha first. Alpha is the probability of type 1 error. All right, which is the probability of rejecting the null hypothesis. That is x bar minus y bar greater than k, given that mu x is equal to mu y. Okay. Okay, guys. Now remember that this is the same as saying that I'm sure you learned in your calculus algebra, or I don't know what course you learned this kind of stuff, but you should, I mean, it's always a good idea to remove the absolute sign. So if you say that the absolute of something is greater than k, that's the same as saying that okay, you see what I've done. So I've used the fact that, excuse me, the absolute value of x bar minus y bar greater than k is the same as saying that x bar 1 minus y bar is greater than k, or x bar minus y bar is less than minus of k, right? So you have two different events, and they are mutually exclusive. So you can write this as the sum of two probabilities. So you can write this as the probability that all right, because you can do this because the two events are mutually exclusive. The event that x bar minus y bar greater than k, and the event that x bar minus y bar less than minus of k are mutually exclusive events. So you can write this as a sum of the two probabilities. Okay, now each of these probabilities, you can work them out in the same way as I did in question 1, example 1. Okay, so this will be n normal with mu x 1 divided by m. This is m, all right? Sorry, excuse me for my writing, not good as always. It's not, it's 1 over m minus normal with mu y 2 over n greater than k, given mu x equal to mu y. Okay, then plus the probability that mu x 1 divided by m minus, so this should be mu y, not mu, excuse me, sorry, this should be y, not x. Mu y 2 divided by m less than minus of k, given mu x equal to mu y. Okay, so this is what you get. Now then this would be the, because once again using the property of independence of the normal variables, you can combine them into one. So the first one will combine into normal with mu x minus mu y as the mean. The variance will be 1 over, sorry, yeah, I know I made this. I'm really sleeping today, I don't know why. It should be n 2 over n, guys, as you noticed already. It should be 2 divided by n. 2 divided by n. Okay. All right. Anyway, so it should be 1 divided by m plus 2 divided by n, right? Greater than k, given that mu x is equal to mu y. All right. That's the first term. The second term is the probability that normal with mu x minus mu y, that's the mean. The variance is 1 over m plus 2 over n less than minus of k, given mu x is equal to mu y. Okay, okay, and so this will be the, now because given the conditioning that mu x is equal to mu y, this would be the probability that a normal variable with 0 mean and variance equal to this is greater than k. We don't need the conditioning anymore, okay, because we used it. And plus the probability that 0 mean and is less than minus of k, right? Okay, guys. Now I'm going to divide both sides by the square root of the variance. So I would do that for each of the two terms. So for the first term, excuse me, my writing is really bad. This is what you get for the first term. And for the second term, you get this. Oh, sorry, I made yet another mistake. Yet another mistake. Sorry, I just found I forgot to divide by this. Sorry. So this should be k divided by the square root of 1 over m plus 2 over n. Okay, and the same thing here, minus k divided by the square root of 1 over m plus 2 over n. Okay. So what you get is a standard normal n01 greater than k times mn okay, and then plus the probability that a standard normal is less than minus of the k of okay, guys. And finally you can write this as 1 minus phi. Phi is the CDF of the standard normal variable. So this would be 1 minus phi of and plus phi at minus okay, so this is the this I know it's been a long calculations, but they're not complicated at all. So as you can see, it's just standard calculation. So this is the expression for alpha, the probability of type 1 error. Any questions on this, guys? Oh, are you okay? Hello, guys. Are you still there or no? Hello? Yes. Oh, are you guys all good? Okay, thank you. All right. So the next thing is to find the beta. So you just do it in the same way. So let me show you how to if I have time. All right, so we've done the alpha so far. So the next thing is to find the probability of type 2 error, which is beta. So it's the probability of accepting, which is the reverse of rejecting. So it's x bar minus y bar less than or equal to k, given that mu x is not equal to mu y. Okay. So this would, again, it's always a good idea to remove the absolute value, to remove the absolute value. So that's what I'm gonna do now. You can, in this case, because x bar minus y bar is less than or equal to k, the rule is like this.
I can learn to understand you much better if I can get familiar with the way you talk.
Sorry, there's a stupid thing coming up. Okay, so because the absolute sign is less than or equal to k, if you remove the absolute sign, what you get is this, that without the absolute sign, x bar minus y bar must be between minus k and plus k. Okay. All right, now this will be the probability that x bar, remember, has a normal distribution with mu x and variance 1 divided by m. Y bar has normal with mu y and 2 divided by n. 2 divided by n less than or equal to k, given that mu x is not equal to mu y. Okay, guys. All right, now because once again they're independent normal variables, so the next step is to write it like minus k less than or equal to normal with mean mu x minus mu y and variance 1 over m plus 2 over n less than or equal to k, right? Given that mu x is not equal to mu y. And the next step is to do the standardization. When I say standardization, you subtract the mean and divide by the standard deviation. So that's what I'm going to do. So I'm going to, first of all, I'm going to subtract the mean, which is this, right? Less than or equal to right? Given that mu x is not equal to mu y. So subtract. So what you get out of this is the probability that minus k minus mu x plus mu y less than or equal to a normal variable with 0 mean and variance 1 over m, 2 over n, less than or equal to k minus mu x plus mu y, right? Given mu x is not equal to mu y. Okay. All right, then the next step, I'm gonna divide by the standard deviation, right? So I'm gonna divide all the terms inside the probability by the standard deviation. So you get minus k minus mu x plus mu y divided by the standard deviation, which is the square root of the variance. Okay, you see that's what I'm doing right now. So I'm dividing all the terms within the brackets by the standard deviation given that mu x is not equal to mu y. Okay, all right. So what you get is the probability that minus k minus mu x plus mu y divided by less than equal to, so the middle term is clearly a standard normal variable, okay, and less than equal to k minus mu x plus mu y less than equal to this is what you get. Okay, now obviously this is we are close to the answer. So the answer is phi at k minus mu x plus mu y divided by the minus phi at right. So this is the answer to the type 2 error probability, or beta. Okay, guys. So let me highlight this. Okay, if you can. All right. Any questions? Any questions on the two examples we done today? So these are like typical. I know there will be no exam for you guys, but I mean, you will find what we are doing today useful when you go to year 2. That's why that's why I'm going on with the online lectures. In addition to the podcast that I have provided you from last year. I think I sent you guys an email some time ago showing you where to find the podcasts from last year. They are on the course website. So on top of that, I'm doing these online lectures because I want you to learn. I want you to learn because that's going to be helpful when you go to year 2 or year 3. I know you're not going to have exams, but learning is always helpful, so okay, guys, any questions you have? Hello, guys. Are you okay? Yeah. So once again, so I think we are almost approaching noon. once again, as I said before, if you haven't completed the UEQ, could you please, because I looked at it this morning, most people haven't done it yet. So could you please do it? It will take you only like 1 or 2 minutes to complete the UEQ. So please, if you haven't done it, I would really, really appreciate if you could do it. As you know, I've been supporting you guys. I'm offering all these online lectures in spite of, I mean, I heard many of the other lecturers are not, they're just playing the podcast from previous years and not offering lectures, but I am giving you lectures every week. So please, please do complete the UQ when you have time. All right, so the next thing today is I'm going to have a tutorial example session from noon to 1 p.m. And then another one from 1 p.m. to 2 p.m. So those example sessions will be on example sheet number 10, which is on the course website. Okay, so could you, all right, let me show you where it is. So let me show you the example sheet number 10. You should be able to see it. I mean, you should be able to see where it is. Here we are. Let me show you. Yeah, it's this one. Okay, this one here. So let me, how do I go back? This one. Stop share. Okay. So the example sheet 10 is over here. This is this one, guys. Okay, it's this one. So can you please look at because I'm going to take a 10 minutes break now. So in that period, can you please look at question one on sheet 10, right? And after I come back, when I come back in 10 minutes time, I will show you how to do it. Okay. All right, guys. So could you please look at this question? Question 1 on sheet 10. Okay. Thank you, guys. I'll see you in 10 minutes time. Okay.